Hi, this is NK Pandey. Today I am going to discuss about second part of the theories of mass transfer. In the first part, I have explained about the film theory and provided derivation for mass transfer coefficient. In today's part, I will be discussing about penetration theory and its complete derivation for mass transfer coefficient. As I have already mentioned earlier, that several theories have been proposed in the past in order to understand the hydrodynamic condition close to the interface, in order to understand the mechanism of mass transfer between the phases. Those theories also provided the expression of mass transfer coefficient in the liquid phase. Let us go through the complete derivation of Higbies penetration theory. And as per Higbies penetration theory, average mass transfer flux is given by this relation, where d is the diffusivity, t is the exposure time, and this is the concentration difference. And this square root term is called mass transfer coefficient. Finally, we get in this way uh, uh, expression for mass transfer flux. So Higby made following assumptions. Each element of the liquid come into contact with interface, and and liquid element stay at interface for a constant period before being replaced by fresh liquid. During their stay at interface, it absorbs gas under unsteady state of absorptions. Uh, so if you see, this is the case of a semi-infinite uh, gas liquid system, where liquid is exposed to a gas containing a solute, and solute is absorbed in the liquid. So what is happening is a liquid element come to the interface, stay for a time period of t, and then finally it transferred to the bulk liquid again. So in this way, each liquid element come to the interface and stay there for a time t, and then finally go to the bulk liquid. And this exposure time for all the liquid element is same as per Higby's assumptions. So let us go through the derivation of this mass transfer flux. This governing equation is given by fixed second law, uh, that is unsteady state diffusion of a component through a medium. This is for one dimensional form. So for solving any differential equation, we should have boundary conditions and initial conditions. Each initial condition is given by at t is equal to 0, Ca is equal to Cab, where Cab is the bulk concentration of component A in the liquid phase. This is for all x. Boundary conditions are given as at x is equal to 0, Ca is equal to Cai. Cai is the interfacial composition of component A for t greater than 0, and at x is equal to infinity, Ca is equal to Cab. Cab is the bulk composition concentration of component A in the liquid phase for all t. Now let us uh, assume a variable uh, uh, such that eta is equal to uh, x divided by 2 square root dA into t. So then let us compute these derivatives. Then computing derivatives. So this we say this is equation number 1. So derivatives of equation 1, del Ca by del t can be written as dca by into del t eta divided by dt, which is equal to, if we write, this can be written as minus x divided by 4 square root dA into t to the power 3 by 2 into c by, again, so del ca by del x can be written as dca by dn into dn by, which can be written as 1 by 2 dA t into second derivative, so that second derivative can be written as 1 by 4 dA t into, so putting these values in equation 1 on substitution in equation 1, so we get minus x divided by 4 square root dA into t 3 by 2 into dca by theta equal to 1 by 4 dA t into, so on simplification we get, so ca plus 2 eta to dca is equal to 0. So this is, we say, this is equation number, we say equation number 2. Now again let u is equal to dc, then equation 2 becomes du theta plus 2 theta into u is equal to, so equation number 3, solving equation number 3 by integrating factor. So integrating factor if can be written as e to the power 2n eta which is equal to e to the power eta square. So multiplying equation 3 by if we get, so plus 2 eta into u into e to the power, or this can be written as u exponential to the power eta square 0. So upon integration we get u to the power eta square is equal to c1, where c1 is the integration constant, or this can be written as dca by eta into equal to c1 e to the power minus eta, where c1 is the integration constant. Again integrating, so we get ca equal to c1 into e to the power minus c2. Again c2 is the second integration constant, can be written as c1 into multiplying both sides by root pi, multiplying and dividing by right hand side, so that plus c2, so that this equation, this term is called error function. This is all error function. So finally, which is denoted by error function RF. So this can be written as CA is equal to pi by 2 into C1 into error function eta plus C2. So this is equation number 4. This was equation number 4, and this is equation number 5. Now we again see the boundary conditions, which says that at x is equal to 0, eta also becomes 0, and CA is equal to CAI, and at x is equal to 0, x is equal to infinity, eta also becomes infinity, then CA is equal to, please note here that error function, property of error function is that f0 is equal to 0, and error function is infinity is given by the root pi by 2. So applying x is equal to 0, that is eta is equal to 0, then finally we get CAI is equal to, so this term becomes 0, that is pi by 2 plus into C1 into 0 plus C2, that means C2 that means C2 becomes CAI. Again at for x is equal to infinity or eta is equal to infinity, then CAB is equal to root I 2 into C1 into 1 plus CAI. CI is this is for C2. So then we get C1 is equal to 2 by pi into CAB minus CAI. So putting the value of C1 and C2, the value of C1 and C2 into equation number 5. X of A at any time t at x is equal to 0 uh, is can be written as minus as per fixed first law. Uh, so earlier we have seen del CA by del x is given by dCA by into, which is nothing but 1 by 2 root dA into t into dCA. You see that? So this putting this value, we get dCA by x is equal to 1 by 2 dA into t into CAB minus CAI into 2 by root I into e to the power minus eta square. So this is converted here actually, this one. So NAT can be given as minus dA 1 by 2 t into CAB minus CAI into 2 by root pi to e to the power minus eta square. This we can equal to 0. Then we get minus dA by pi t into, after simplification we get CAB minus CAI or written at any time t can be written as dA square root into CAI minus CAB. So average nodal flux average can be written as 1 by divided by T is exposure time. So 0 to T and the square root dA by pi T into CAI minus CAB into D2. So we get NA average given by 2 into the square root dA by pi T into CAI minus CAB. So, so this is that the required solution of diffusion equation or second law in the light of Higbies penetration theory. And if this concentration versus distance at various time it is plotted, this is x and this is CAI. So we get first one is at t is equal to 0 and this is at a smaller time, this is at bigger time. So so this is, you can say this is T1, this is T2 and this is T3, where T3 greater than T2 greater than T1. And one thing is to be noted that this Higbies penetration theory hydrodynamic condition considered is a plug flow very similar to analogous to plug flow condition. In the next video, we will go through this Danckwert's surface renewal theory derivation. And thank you very much for kind attention.